Tonight, we're going to confront something that will completely shatter your understanding of how big things can get in the universe. You think you know what large means. You've seen images of galaxies, maybe even tried to wrap your mind around their scale. But there's a structure out there, a galaxy discovered just recently, that makes even the largest galaxies we knew about look small by comparison. It's so vast that if you could somehow travel at the speed of light, it would take you over 16 million years just to cross from one side to the other. And by the end of tonight, you're going to understand not just how impossibly large this galaxy is, but why its existence challenges everything we thought we knew about how galaxies grow and what limits their size. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky, you are seeing the Milky Way from the inside. That faint band of light stretching across the darkness, that is our galaxy, our home. 100,000 light years from edge to edge, containing somewhere between 200 billion and 400 billion stars, along with the Sun, along with Earth, along with everything humanity has ever known. To give you some sense of what 100,000 light years means, imagine you could travel at the speed of light. You would be moving at 186,000 miles every single second. At that speed, you could circle Earth 7.5 times in 1 second. And yet, even at this incredible speed, it would take you 100,000 years to cross from one side of the Milky Way to the other. If you started this journey when modern humans first appeared on Earth, roughly 300,000 years ago, you would only be about 1/3 of the way across. The Milky Way is genuinely vast. From our perspective here on Earth, it is almost incomprehensibly large. And yet, as we are about to discover, it is actually quite small compared to the largest structures in the universe. For a very long time, people believed the Milky Way was the entire universe. Everything. There was nothing beyond it. In the early 1900s, astronomers debated whether fuzzy patches of light they could see through telescopes were nebulae within our galaxy or entirely separate galaxies beyond it. The Great Debate, as it became known, was settled in 1924 when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe individual stars in what we now call the Andromeda galaxy. He proved definitively that Andromeda was far outside the Milky Way, a separate galaxy entirely, roughly 2.5 million light-years away. This discovery changed everything. The universe was suddenly far larger than anyone had imagined. The Milky Way was not alone. It was one galaxy among many. And as telescopes improved, astronomers discovered more and more galaxies. Thousands, then millions, then billions. And today, we estimate there are roughly 2 trillion galaxies in the observable universe. Each one a massive collection of stars, gas, dust, and dark matter. And among these 2 trillion galaxies, sizes vary dramatically. Some galaxies are tiny, containing just a few million stars and spanning only a few thousand light-years. These are called dwarf galaxies, and they are actually the most common type in the universe. Most galaxies are small. Then, there are galaxies like the Milky Way, large spiral galaxies containing hundreds of billions of stars. These are less common, but still fairly ordinary in the grand cosmic scheme. And then there are the giants, galaxies so enormous that they dwarf even large spirals like the Milky Way. Galaxies that contain not billions, but trillions of stars. Galaxies that stretch not for 100,000 light-years, but for millions of light-years. These are the true monsters of the cosmos. And the biggest one we have ever found is called Alcyoneus. Now, before we dive into Alcyoneus specifically, let me give you some context about what we are dealing with here. Throughout the history of astronomy, as our telescopes have improved, we have consistently found that the universe is larger and more complex than we previously thought. Every time we build a more powerful telescope, we discover structures that dwarf what we knew before. In the 1920s, when Hubble proved that Andromeda was a separate galaxy, the largest known structures were galaxy groups containing a few dozen galaxies. By the 1950s, astronomers had discovered galaxy clusters containing thousands of galaxies. By the 1980s, they had mapped superclusters containing thousands of clusters, and by the 2000s, they had discovered great walls, enormous filaments of galaxies stretching hundreds of millions of light-years. Each discovery pushed the limits of what we thought possible. And Alcyoneus is the latest in this series of discoveries, a structure that redefines our understanding of how large a single galaxy can be. Before we get to Alcyoneus, we need to understand what makes a galaxy big, because size in astronomy is not always straightforward. When we talk about a galaxy's size, we are usually talking about the diameter of its visible structure, the region where most of its stars are located. For the Milky Way, that is about 100,000 light-years. But galaxies are not solid objects with sharp edges. They fade gradually at their boundaries, becoming less and less dense until you cannot really say where the galaxy ends and intergalactic space begins. Some galaxies also have extended structures that go far beyond their main bodies. These structures, called radio lobes, are created by supermassive black holes at the centers of galaxies. When matter falls into these black holes, it does not all get swallowed. Some of it gets accelerated to nearly the speed of light and shot out in two opposite directions as jets of particles and energy. These jets can extend for millions of light-years beyond the galaxy itself. The particles in the jets interact with magnetic fields and emit radio waves, which is how we detect them. These radio lobes can make a galaxy's total size much, much larger than the visible galaxy alone. To understand how radio lobes form, we need to talk about supermassive black holes and accretion disks. Every large galaxy has a supermassive black hole at its center. The one at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million times the mass of the Sun. That might sound enormous, and it is by human standards, but it is actually quite small for a supermassive black hole. Some black holes at the centers of galaxies have masses of billions or even tens of billions of solar masses. Most of the time, these black holes are quiet. They are not actively feeding on material, so they produce very little radiation. But sometimes, gas and dust from the surrounding galaxy falls toward the black hole. As this material spirals inward, it forms an accretion disk, a flat disk of matter orbiting the black hole at tremendous speeds. The particles in the disk are moving so fast and are packed so tightly that friction heats them to millions of degrees. At these temperatures, the disk glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays. The brightest active galactic nuclei can outshine all the stars in their host galaxies combined. We are talking about a region no larger than our solar system, producing more light than hundreds of billions of stars. But not all the material in the accretion disk falls into the black hole. Some of it gets caught up in the black hole's magnetic field. Black holes themselves do not have magnetic fields, but the swirling plasma in the accretion disk does. This plasma is composed of ionized gas that has been heated so much that electrons have been stripped away from atoms, leaving charged particles. These charged particles interact with magnetic fields, and as they spiral around the field lines, they can be accelerated to tremendous speeds. Near the poles of the black hole, where the magnetic field lines are most concentrated, some of this material gets funneled into narrow jets. These jets shoot outward in opposite directions, perpendicular to the accretion disk. The particles in the jets are moving at 99% of the speed of light or faster. At these relativistic speeds, the normal laws of physics start behaving strangely due to Einstein's theory of relativity. Time slows down for the particles. Distances contract, and the energy carried by the jets becomes truly enormous. A single jet from an active galactic nucleus can carry more energy than 1 billion supernovae. These jets plow through the intergalactic medium, the thin gas that exists between galaxies. Now, with that background, let me tell you about Alcyoneus. Alcyoneus is one of these galaxies. It is a giant elliptical galaxy located roughly 3 billion light-years from Earth in the constellation Lynx. The galaxy itself, the main body containing most of its stars, is large, but not exceptionally so. It is about 660,000 light-years across, roughly 6.5 times the diameter of the Milky Way. That is big, but there are other galaxies with larger main bodies. What makes Alcyoneus special, what makes it the biggest galaxy we have ever discovered, are its radio lobes. The jets from Alcyoneus's central black hole have created 2 enormous lobes extending in opposite directions from the galaxy. These lobes stretch for 16.3 million light-years from end to end. 16.3 million light-years. To put that in perspective, the Milky Way is 100,000 light-years across. Alcyoneus is 163 times longer. If the Milky Way were the size of a grain of rice, Alcyoneus would be the length of a football field. Actually, longer than a football field, more like the length of a city block. The Andromeda galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. Alcyoneus is more than 6 times longer than the distance between the Milky Way and Andromeda. If Alcyoneus were positioned with one end at the Milky Way, the other end would extend far beyond Andromeda, past the entire local group of galaxies, reaching into the space between galaxy groups. This is a structure so vast it challenges comprehension. Light itself, traveling at 186,000 miles per second, takes 16.3 million years to cross from one end of Alcyoneus to the other. If you started at one end and could somehow travel at the speed of light, by the time you reached the other end, 16.3 million years would have passed. For context, 16.3 million years ago on Earth, our human ancestors had not yet appeared. The earliest hominins would not evolve for another 10 million years. The continents were still in different positions. The climate was completely different, and light that left one end of Alcyoneus back then is only now reaching the other end. Now, you might be wondering how such a structure can even exist. How can jets of particles travel millions of light-years through space? What prevents them from dispersing or being disrupted? The answer has to do with the power of the central black hole and the nature of the intergalactic medium. The supermassive black hole at the center of Alcyoneus is feeding on gas and dust from the surrounding galaxy. As matter spirals into the black hole, it forms an accretion disk, a swirling disk of material orbiting the black hole at tremendous speeds. The friction in this disk heats the material to millions of degrees, causing it to emit intense radiation. Some of this material does not fall into the black hole. Instead, it gets channeled along the black hole's magnetic field lines and accelerated to nearly the speed of light. This creates two narrow jets, shooting out in opposite directions, perpendicular to the accretion disk. These jets are incredibly powerful. The energy output from an active galactic nucleus like this can exceed the energy output of all the stars in the galaxy combined. We are talking about energies that dwarf anything we encounter in normal stellar processes. The jets plow through the intergalactic medium, the thin gas that exists between galaxies. As they do, they push this gas aside, creating vast bubbles. These bubbles are the radio lobes we observe. The particles in the jets are mostly electrons and protons moving at relativistic speeds. When these particles interact with magnetic fields in the intergalactic medium, they emit synchrotron radiation, which we detect as radio waves. This is how we know the lobes are there. They are invisible to optical telescopes, but they glow brightly at radio wavelengths. What is remarkable is that the jets can remain coherent and focused across such enormous distances. You might think that a jet of particles would spread out and dissipate over millions of light years, but the magnetic fields associated with the jets help keep them collimated, preventing them from spreading too much. The jets from Alcyoneus have been active for a very long time. To create lobes this large, the black hole must have been actively feeding and producing jets for tens of millions of years at least, possibly hundreds of millions of years. This is a time scale that is hard to grasp. Human civilization is only a few thousand years old. Our species has existed for only a few 100,000 years. The jets from Alcyoneus have been streaming across space for a duration that makes the entire history of humanity look like an eye blink. Alcyoneus was discovered in 2021 by a team of astronomers led by Martijn Ooi at Leiden University in the Netherlands. They found it by analyzing data from the LOFAR radio telescope, the low-frequency array, which is specifically designed to detect the kind of low-frequency radio emissions produced by these giant radio lobes. The discovery was somewhat serendipitous. Alcyoneus was not particularly bright or prominent in radio observations. It was just one of many radio galaxies in the survey data. But when the team measured the full extent of its lobes, they realized they had found something extraordinary. At the time of its discovery, Alcyoneus broke the previous record for the largest known galaxy structure. That record had been held by another radio galaxy with lobes extending about 15 million light-years. Alcyoneus is about 8% larger, which might not sound like much, but at this scale, even a small percentage difference represents hundreds of thousands of light-years. What makes this discovery particularly interesting is that Alcyoneus is not exceptionally massive or bright. The galaxy itself is fairly typical for a giant elliptical. Its central black hole is large, probably around 400 million times the mass of the Sun, but that is not unusually large for galaxies of this type. Some supermassive black holes are billions of times the mass of the Sun. So why did Alcyoneus grow so large? The answer seems to be a combination of factors. First, the galaxy is located in a relatively low-density environment. The intergalactic medium around it is thinner than average, which means the jets encounter less resistance as they expand. In denser environments, jets are more likely to be disrupted or compressed by the surrounding gas. Second, Alcyoneus appears to have been producing jets steadily for a very long time without major interruptions. Many active galactic nuclei go through cycles where the jets turn on and off as the black hole's feeding rate changes. Alcyoneus seems to have maintained a relatively constant output, allowing the lobes to grow continuously. Third, the orientation of the galaxy may play a role. The jets happen to be oriented in a direction where there are no major structures to block or deflect them. They have had a clear path through space for millions of light years. It is also worth noting that Alcyoneus is not unique in having massive radio lobes. There are other radio galaxies with lobes extending millions of light years. Alcyoneus is simply the largest we have found so far. As our radio telescopes improve and we survey more of the sky, we may discover even larger structures. In fact, there is no fundamental physical limit preventing radio lobes from growing even larger than Alcyoneus. The main limitations are the longevity of the jets and the density of the surrounding environment. A galaxy in an even emptier region of space, with jets that have been active even longer, could potentially have lobes stretching 20 million light-years or more. Now, let me explain in more detail what these radio lobes actually are and how they maintain their structure over such vast distances. The lobes are not solid objects. They are regions of space filled with high-energy particles and magnetic fields. When the jets from the central black hole shoot out into space, they are carrying electrons and other charged particles moving at 98 or 99% of the speed of light. These are called relativistic speeds. Speeds where the effects of Einstein's special theory of relativity become significant. At relativistic speeds, strange things happen. Time slows down for the moving particles compared to stationary observers. The particles' mass effectively increases, and the energy they carry becomes enormous. As these relativistic particles plow into the intergalactic medium, they create a shock wave, like the bow wave of a ship moving through water. Behind this shock, a bubble forms, filled with the particles from the jet. This bubble is the radio lobe. The particles in the lobe are trapped by magnetic fields. As they spiral around these magnetic field lines, they emit synchrotron radiation. Synchrotron radiation is electromagnetic radiation produced when charged particles are accelerated in a magnetic field. The frequency of the radiation depends on the strength of the magnetic field and the energy of the particles. In the case of radio lobes, the particles are so energetic and the magnetic fields are strong enough that the synchrotron radiation is produced at radio wavelengths. This is why we call them radio lobes. They glow brightly at radio frequencies, even though they are invisible to optical telescopes. Over time, the particles in the lobes lose energy. As they emit synchrotron radiation, they slow down. This means that radio lobes fade over time. If the jets shut off and stop supplying fresh high-energy particles, the lobes will gradually dim and eventually become undetectable. The fact that Alcyoneus's lobes are still bright means the jets are still active, still pumping energy into the lobes. This is happening right now, even as we speak, or rather, it was happening 3 billion years ago, when the light we are now observing left Alcyoneus. The pressure inside the lobes is higher than the pressure in the surrounding intergalactic medium. This pressure difference helps keep the lobes inflated, like a balloon. If the pressure inside dropped, the lobes would collapse. But as long as the jets keep supplying energy and particles, the pressure remains high enough to maintain the structure. One of the fascinating aspects of radio galaxies is that the lobes can tell us about the history of the jet activity. Sometimes you can see multiple lobes or complex structures that indicate the jets have turned on and off multiple times, or that the direction of the jets has changed. In Alcyoneus, The lobes appear relatively smooth and symmetric, suggesting steady, continuous jet activity. But in other radio galaxies, the lobes show knots, bends, and irregularities that reveal a more turbulent history. Radio lobes can also interact with their environment in interesting ways. If a lobe expands into a region where the intergalactic medium is denser, it will slow down and may even be compressed. If it expands into a void where the medium is especially thin, it can grow more rapidly. The shape and extent of radio lobes therefore provide clues about the structure of the intergalactic medium, which is otherwise difficult to study because it is so diffuse. Alcyoneus's enormous lobes tell us that it has been fortunate enough to expand into a particularly empty region of space. If it were in a denser environment, the lobes would be smaller, compressed by the surrounding gas. But in its sparse neighborhood, the lobes have been free to grow to record-breaking sizes. This makes Alcyoneus not just a curiosity, but a valuable tool for understanding the intergalactic medium and the physics of relativistic jets. By studying Alcyoneus and other radio galaxies, astronomers can learn about some of the most extreme phenomena in the universe: supermassive black holes, relativistic jets, magnetic fields, and the near-empty spaces between galaxies. But a galaxy in an even emptier region of space, with jets that have been active even longer, could potentially have lobes stretching 20 million light-years or more. But before we go any further, let us talk about other enormous galaxies, because Alcyoneus is not the only giant out there. When we talk about the biggest galaxies by their main stellar bodies, rather than their radio lobes, different galaxies take the title. The largest galaxy, by stellar extent, is IC 1101. This is a supergiant elliptical galaxy located about 1.07 billion light-years away in the constellation Virgo. IC 1101 is approximately 6 million light-years across. That is 60 times the diameter of the Milky Way. If IC 1101 were positioned where the Milky Way is, it would stretch far beyond Andromeda. The entire local group of galaxies, which includes the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, would fit inside IC 1101 with room to spare. This galaxy contains roughly 100 trillion stars. For comparison, the Milky Way has between 200 billion and 400 billion stars. IC 1101 has about 250 times more stars than the Milky Way. Think about that. Every star you see in the night sky, every constellation, every nebula observed by telescopes, all of it is contained within the Milky Way. Now imagine a galaxy with 250 times more stars. The sheer number becomes almost meaningless because our brains cannot really grasp what 100 trillion stars looks like. IC 1101 did not start out this large. It grew through a process called galactic cannibalism. The galaxy sits at the center of a galaxy cluster called Abell 2029. Galaxy clusters are violent places where galaxies regularly pass close to each other. When they do, the larger galaxy's gravity can strip stars away from smaller galaxies. Over billions of years, a galaxy at the center of a cluster can consume dozens or even hundreds of smaller galaxies, growing larger and larger with each merger. IC 1101 has been doing this for billions of years. It is the gravitational bully of its neighborhood, pulling in any galaxy that comes too close. The result is a bloated, enormous elliptical galaxy packed with stars. The process of galaxy cannibalism is both violent and beautiful when viewed on cosmic timescales. When a smaller galaxy approaches IC 1101, it does not crash into it like two cars colliding. Instead, gravity does the work. As the smaller galaxy gets closer, IC 1101's gravity begins to pull stars away from it. The outer regions of the smaller galaxy are pulled harder than the core because they are closer to IC 1101. This creates tidal forces, the same type of forces that cause ocean tides on Earth, just on a vastly larger scale. These tidal forces stretch the smaller galaxy, pulling it into long streamers of stars. Eventually, these streams wrap around IC 1101, and over hundreds of millions of years, the orbits of the captured stars are randomized. They become part of IC 110's stellar population, indistinguishable from stars that were there originally. The smaller galaxy effectively disappears, absorbed entirely into the giant. And IC 1101 has done this not once or twice, but dozens or perhaps hundreds of times. Every dwarf galaxy that wandered too close got consumed. Every smaller elliptical that strayed into IC 1101's gravitational influence got torn apart and absorbed. Over billions of years, all those consumed galaxies added up, building IC 1101 into the supergiant it is today. The interesting thing is that this process is still happening. IC 1101 is still consuming galaxies right now. If we could watch it for a few 100 million years, we would see new tidal streams forming as fresh galaxies are torn apart. We would see IC 1101 growing larger with each merger. Galaxy cannibalism is not unique to IC 1101. It happens throughout the universe, wherever galaxies interact. The Milky Way itself is consuming several smaller galaxies right now. The Sagittarius Dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity. Its stars are being stripped away and incorporated into our galaxy's halo. The Canis Major Dwarf galaxy is undergoing the same fate. Even the Large Magellanic Cloud and the Small Magellanic Cloud, two of our nearest galactic neighbors, will eventually be consumed by the Milky Way. In about 2.5 billion years, the Large Magellanic Cloud will collide with the Milky Way, and its stars will become part of our galaxy. So the process that built IC 1101 into a giant is the same process that the Milky Way is engaging in right now, just on a smaller scale. The difference is that IC 1101 sits at the center of a rich galaxy cluster, where interactions are far more common. The Milky Way is in a relatively sparse region of space, so it encounters smaller galaxies less frequently. If the Milky Way were in IC 1101's position, it too might have grown into a supergiant by now. Location matters in galaxy evolution. Galaxies in dense environments grow faster because they have more neighbors to consume. Galaxies in sparse environments grow more slowly because encounters are rare. If you were somehow standing on a planet near the center of IC 1101, your night sky would be incredible. The density of stars near the galaxy's core is thousands of times higher than in the Milky Way. You would see stars in every direction, many of them close enough to shine as brightly as Venus or Jupiter appear in our sky. There would be no dark patches, no empty spaces. The entire sky would glow with starlight. Constellations would be meaningless because individual stars would be impossible to distinguish. The sky would be a nearly continuous wash of light. But IC 1101 is not the only supergiant elliptical. There is M87, located in the Virgo cluster about 53 million light-years away. M87 is roughly 120,000 light-years across, similar in diameter to the Milky Way, but it contains about 1 trillion stars, roughly 3 to 5 times more than the Milky Way. There is M87, located in the Virgo cluster about 53 million light-years away. M87 is a fascinating galaxy for multiple reasons, and it deserves a closer look because it represents another extreme in the universe. M87 is roughly 120,000 light-years across, similar in diameter to the Milky Way, but it contains about 1 trillion stars, roughly 3 to 5 times more than the Milky Way. The galaxy is classified as a supergiant elliptical, and it sits at the heart of the Virgo cluster, dominating its surroundings. But what makes M87 truly famous is its supermassive black hole. In April 2019, the Event Horizon Telescope collaboration made history by releasing the first ever direct image of a black hole's event horizon. That black hole was the one at the center of M87. The image showed a bright ring of glowing gas surrounding a dark central region, the black hole's shadow. It was a triumph of observational astronomy, confirming decades of theoretical predictions about what black holes should look like. The black hole at the center of M87 has a mass of about 6.5 billion times the mass of the Sun. To put that in perspective, the black hole at the center of the Milky Way, Sagittarius A, has a mass of only about 4 million solar masses. M87's black hole is over 1,600 times more massive. This enormous black hole has an event horizon, the boundary beyond which nothing can escape. That is about 23.6 billion miles across. That is roughly 250 times the distance from the Sun to Earth. If you place this black hole at the center of our solar system, its event horizon would extend far beyond the orbit of Neptune, engulfing all the planets. The event horizon defines the point of no return. Once anything crosses this boundary, whether matter or light, it can never escape. The gravity is so strong that the escape velocity exceeds the speed of light, and since nothing can move faster than light, nothing can get out. The ring of light in the Event Horizon Telescope image is not the event horizon itself. It is the photon ring, a region just outside the event horizon where light orbits the black hole before either escaping or falling in. This light comes from the accretion disk, the swirling disk of superheated gas orbiting the black hole. The dark region in the center of the image is larger than the event horizon itself. It is the black hole's shadow, which includes both the event horizon and a region around it where light is so strongly bent by gravity that it falls into the black hole. Creating this image required an extraordinary international effort. The Event Horizon Telescope is not a single telescope, but a global network of radio telescopes working together. By combining observations from telescopes in locations around the world, from Hawaii to Chile to Antarctica, astronomers created an effective telescope the size of Earth. This technique, called very long baseline interferometry, allowed them to achieve the angular resolution needed to see details as small as the event horizon of M87's black hole. Even with an Earth-sized telescope, M87's black hole only appears as a tiny speck in the sky. The angular size is about 40 microarcseconds. To understand how small that is, imagine looking at a donut on the surface of the moon. That is roughly the angular size of M87's black hole shadow as seen from Earth. The fact that we can resolve such a small feature from 53 million light-years away is a testament to the power of modern observational techniques. M87 is also a powerful radio source. Like Alcyoneus, M87 has jets produced by its supermassive black hole. These jets are not as large as Alcyoneus's, extending only about 5,000 light-years from the galaxy, but they are still enormous by any reasonable standard. 5,000 light-years is 50 times the distance from Earth to the nearest star after the Sun. The jets from M87 move at relativistic speeds, just like those from Alcyoneus. Matter in the jets travels at more than 98% the speed of light. These jets are some of the fastest phenomena in the universe, and they carry enormous amounts of energy away from the black hole. The power output of M87's jets is difficult to comprehend. They are releasing energy at a rate that exceeds the total power output of all the stars in the Milky Way. And this energy comes from a region no larger than our solar system. The central engine, the supermassive black hole, and its accretion disk, is incredibly compact compared to the galaxy as a whole, but it outshines hundreds of billions of stars. One of the mysteries about supermassive black holes is how they grew so large. 6.5 billion solar masses is an incredible amount of mass to accumulate. If the black hole at the center of M87 grew by consuming matter at the maximum possible rate, called the Eddington limit, it would still take billions of years to reach its current mass. And yet, we know that supermassive black holes existed when the universe was very young, less than 1 billion years old. Some of these early black holes already had masses of billions of solar masses. How did they grow so fast? This is one of the major unsolved questions in astrophysics. There are several theories. Perhaps supermassive black holes started from seeds that were already quite massive, maybe hundreds or thousands of solar masses, rather than growing from stellar mass black holes. Or perhaps in the early universe, black holes could grow faster than the Eddington limit under certain conditions. Or perhaps multiple black holes merged together in the dense cores of early galaxies, rapidly building up mass. The truth is, we do not fully understand how supermassive black holes formed and grew, and galaxies like M87, with their enormous central black holes, are key to unraveling this mystery. M87 has another claim to fame. It is one of the brightest sources of X-rays in the sky. X-rays are produced by gas that has been heated to millions of degrees. In M87, this hot gas fills the space around the galaxy, forming what is called a hot gaseous halo. This halo contains as much mass as all the stars in the galaxy combined. It is held in place by the gravity of M87 and the dark matter halo surrounding the galaxy. The hot gas in this halo glows brightly at X-ray wavelengths, making M87 easily detectable by X-ray telescopes. Studying this hot gas tells us about the history of the galaxy. The gas was heated by supernova explosions and by energy from the central black hole's jets. Over billions of years, these processes have pumped enormous amounts of energy into the gas, keeping it hot and preventing it from cooling and forming new stars. This is why M87, like most elliptical galaxies, is not forming many new stars. The gas is too hot to collapse and ignite star formation. In this sense, the black hole is regulating the galaxy's growth. By heating the surrounding gas, it prevents new stars from forming, which in turn reduces the amount of gas that can eventually fall into the black hole. It is a form of feedback, where the black hole's activity affects its own food supply. Understanding this feedback process is crucial to understanding how galaxies evolve. And M87, with its powerful black hole, and well-studied hot gas halo is one of the best laboratories for studying these processes. So while M87 might not have the largest stellar extent among galaxies, it is nevertheless an extreme object. Its supermassive black hole is one of the most massive known. Its jets carry incredible amounts of energy. Its hot gas halo glows brightly at X-rays, and it was the first galaxy where we directly imaged a black hole's event horizon. M87 represents the upper end of what black holes and their host galaxies can become. More importantly, M87 is famous for its supermassive black hole. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole, and that black hole was at the center of M87. The black hole has a mass of about 6.5 billion times the mass of the Sun. For comparison, the black hole at the center of the Milky Way, Sagittarius A, has a mass of only about 4 million solar masses. M87's black hole is over 1,600 times more massive. This black hole also produces jets, though not as large as Alcyoneus. The jets from M87 extend about 5,000 light-years from the galaxy, still enormous by human standards, but small compared to Alcyoneus's 16 million light-year span. Then there is A2261-BCG, located about 3 billion light-years away at the center of the galaxy cluster Abell 2261. This galaxy is roughly 2 million light-years across, 20 times the diameter of the Milky Way. It contains an estimated 10 trillion stars. Again, these numbers start to lose meaning. 10 trillion stars. What does that even look like? If you tried to count to 10 trillion, counting one number per second without stopping, it would take you over 300,000 years. These supergiant galaxies are among the most massive objects in the universe. They represent the upper end of galaxy sizes, the absolute largest structures that gravity can hold together. But here is something crucial to understand. These galaxies are rare, extremely rare. Out of the 2 trillion galaxies in the observable universe, only a tiny fraction are supergiants like IC 1101 or A2261-BCG. Most galaxies are much smaller. In fact, the vast majority of galaxies are dwarf galaxies, small structures containing just a few million to a few billion stars and spanning only a few thousand light-years. Let me give you some specific examples to drive this point home. The Segway, one galaxy, is one of the smallest known galaxies. It contains only about 1,000 stars, and it is just a few hundred light-years across. That is barely a galaxy at all. It is more like a large star cluster. Segway. One orbits the Milky Way as a satellite galaxy, held in orbit by our galaxy's gravity. And there are dozens of galaxies like Segway, one orbiting the Milky Way. Tiny, faint, containing very few stars. The Large Magellanic Cloud, one of our nearest galactic neighbors, visible to the naked eye from the southern hemisphere, contains about 10 billion stars. That sounds like a lot, and it is. But it is only about 2 to 5% of the number of stars in the Milky Way. The Large Magellanic Cloud is about 14,000 light-years across, roughly 1/7 the diameter of the Milky Way. It is a substantial galaxy, but it is dwarfed by the Milky Way. The Small Magellanic Cloud is even smaller, containing only about 3 billion stars and spanning about 7,000 light-years. And these are among the larger dwarf galaxies. Most dwarf galaxies are much smaller and fainter than the Magellanic Clouds. The Ursa Major 1 dwarf galaxy contains only about 10,000 stars. The Draco dwarf spheroidal galaxy contains about 400,000 stars. The sculptor dwarf galaxy contains about a few million stars. All of these are satellites of the Milky Way, orbiting around us, held in place by gravity. And this pattern repeats throughout the universe. Every large galaxy is surrounded by dozens or even hundreds of dwarf galaxies. Andromeda has its own collection of satellite galaxies. M87 has dozens of dwarfs orbiting it. Wherever there is a large galaxy, there are many small ones nearby. Dwarf galaxies are by far the most common type of galaxy in the universe. If you randomly selected 1,000 galaxies from across the cosmos, probably 900 or more would be dwarfs. Only a small minority would be large spirals, like the Milky Way, or large ellipticals, like M87. And only a tiny fraction would be supergiants, like IC1101. This is important to understand because it puts the Milky Way's size into proper context. When most people hear about giant galaxies like IC1101, they often come away thinking that the Milky Way is small, and, compared to IC1101, it is. But IC1101 is exceptionally rare. It is an outlier, not the norm. The typical galaxy is far smaller than the Milky Way. Most galaxies would look up at the Milky Way with envy, if galaxies could have feelings. The Milky Way, with its 100,000 light-year diameter and hundreds of billions of stars, is actually quite large compared to most galaxies. If you randomly selected 1,000 galaxies from the universe, probably 950 of them would be smaller than the Milky Way. Maybe 40 would be roughly similar in size. And only about 10 would be larger, with just 1 or 2 being dramatically larger like IC1101. The Milky Way is not in the top 1% of galaxy sizes, but it is comfortably in the top 5%. That makes it large, genuinely large by cosmic standards. We are not living in some tiny, insignificant corner of the universe. Our galaxy is one of the bigger ones that exist. But compared to the absolute giants, the IC1101s and the Alcyoneus, the Milky Way is small. Not tiny, not insignificant, but definitely small. And when we zoom out even further, when we look at structures larger than individual galaxies, the Milky Way becomes even smaller in comparison. Galaxies are not randomly scattered through space. They cluster together due to gravity. The Milky Way is part of a small cluster called the Local Group, which contains about 50 galaxies. Most of these are dwarf galaxies. The only large galaxies in the Local Group are the Milky Way, Andromeda, and the Triangulum galaxy. The entire Local Group spans about 10 million light-years across. That might sound enormous, and by human standards it certainly is, but in cosmic terms, it is just a small cluster. There are galaxy clusters that are much, much larger. The Virgo cluster, for example, is one of our nearest large galaxy clusters. It sits about 53 million light-years away and contains somewhere between 1,300 and 2,000 galaxies. The Virgo cluster spans about 15 million light-years across. At its center sits M87, the giant elliptical galaxy we talked about earlier. M87 dominates the Virgo cluster, its gravity holding the cluster together. The Coma cluster is even larger, containing over 1,000 large galaxies and potentially tens of thousands of smaller dwarf galaxies. It spans about 20 million light-years across and sits about 320 million light-years from Earth. The Coma cluster is one of the densest concentrations of galaxies we know of. In regions like the Coma cluster core, galaxies are packed so tightly that collisions and interactions are common. This is where giant elliptical galaxies, like IC1101 form, growing large by consuming their neighbors. But galaxy clusters are not the end of the story. Clusters themselves group together into superclusters. The local group is part of a much larger structure called the Virgo supercluster. The Virgo supercluster contains about 100 galaxy groups and clusters, including the massive Virgo cluster, which gives the supercluster its name. The Virgo supercluster spans about 110 million light-years. To put that in perspective, light takes 110 million years to cross from one side of the Virgo supercluster to the other. 110 million years ago on Earth, dinosaurs were still tens of millions of years away from evolving. The first mammals were small, shrew-like creatures. The continents were arranged differently than they are today. And light, leaving one edge of the Virgo supercluster back then, is only now reaching the opposite edge. Within the Virgo supercluster, the local group is not particularly special. We are on the outskirts, in a relatively sparse region. The action, the dense concentrations of galaxies, the massive clusters, those are all closer to the center, near the Virgo cluster itself. We are suburbanites in the cosmic landscape. But even the Virgo supercluster is part of something larger. In 2014, astronomers published a study that redefined our understanding of large-scale structure. Using data from thousands of galaxies, they mapped out the flow of galaxies through space. Galaxies are not stationary. They are moving, pulled by the gravity of surrounding mass. By analyzing these motions, the researchers discovered that the Virgo supercluster is actually part of an even larger structure. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster, a collection of multiple superclusters, all flowing toward a common gravitational center. It spans approximately 520 million light-years and contains roughly 100,000 galaxies. Think about that for a moment. 100,000 galaxies, each containing millions, billions, or even trillions of stars. All of them bound together, however loosely, by gravity into a single vast structure. The Milky Way is one tiny piece of Laniakea, one galaxy among 100,000. At the heart of Laniakea is a region of space called the Great Attractor. The Great Attractor is a massive concentration of mass, probably composed of multiple galaxy clusters, that is pulling everything in the Laniakea supercluster toward it. The Milky Way is moving toward the Great Attractor at a speed of about 373 miles per second. That is over 1.34 million miles per hour. We are racing through space at incredible speed, pulled by the gravity of a structure we can barely see because it lies behind the plane of our own galaxy, hidden by dust and gas. The discovery of the Great Attractor was one of the great mysteries of astronomy in the 1970s and 80s. Astronomers could measure the motion of galaxies and determine that something massive was pulling us, but they could not see what it was. The region lies in what is called the zone of avoidance, an area of sky blocked by the Milky Way's disk. Only in recent decades, using X-rays, infrared, and radio waves that can penetrate the dust, have astronomers been able to map out the Great Attractor and understand what is pulling us. It turns out to be a combination of several massive galaxy clusters, including the Norma cluster, along with even larger structures beyond, like the Shapley supercluster. The Shapley supercluster sits about 650 million light-years away and contains over 8,000 galaxies. It is one of the most massive structures in the nearby universe, and its gravity is strong enough to influence the motions of galaxies hundreds of millions of light-years away. Even Laniakea itself is being pulled toward the Shapley supercluster. At every scale, there is always something larger. The local group is part of a much larger structure called the Virgo supercluster. The Virgo supercluster contains about 100 galaxy groups and clusters, including the massive Virgo cluster, which contains thousands of galaxies. The Virgo supercluster spans about 110 million light-years. Within this structure, the local group is just a tiny, outlying member, a small collection of galaxies on the outskirts of a much larger organization. But even the Virgo supercluster is part of something larger. In 2014, astronomers discovered that the Virgo supercluster is itself just a small part of an even larger structure called Laniakea. Laniakea is a supercluster, a collection of multiple superclusters. It spans approximately 520 million light-years and contains roughly 100,000 galaxies. The name Laniakea means immeasurable heaven in Hawaiian, which is fitting given its enormous size. To understand Laniakea, you have to think about how galaxies move. Galaxies are not stationary. They are moving through space, pulled by the gravity of surrounding mass. By mapping the motion of galaxies, astronomers can determine which large-scale structures they belong to. Laniakea represents a region of space where all the galaxies are moving toward a common gravitational center called the Great Attractor. The Milky Way, along with the local group and the Virgo supercluster, is all flowing toward the Great Attractor at a speed of about 373 miles per second. Within Laniakea, the Milky Way is nothing special. It is one galaxy among 100,000, a single grain of sand on a beach. And Laniakea itself is just one supercluster among many. The universe is filled with these enormous structures, superclusters separated by vast voids, empty regions of space where very few galaxies exist. At the largest scales, the universe looks like a cosmic web. Filaments of galaxies stretching across hundreds of millions or even billions of light-years, connected by threads and separated by enormous voids. There is the Sloan Great Wall, a structure discovered in 2003 that stretches about 1.37 billion light-years across. It is a wall of galaxies, a sheet of matter extending across more than 1 billion light-years of space. If the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. Then there is the Hercules-Corona Borealis Great Wall, discovered in 2013. This structure is even larger, spanning about 10 billion light-years. 10 billion light-years. That is about 1/10 the diameter of the observable universe. The Hercules-Corona Borealis Great Wall is so large that light takes 10 billion years to cross it. For perspective, the universe itself is only 13.8 billion years old. This structure formed when the universe was quite young, and it has been growing ever since. Structures like these challenge our understanding of how the universe formed. According to cosmological models, there should be a limit to how large structures can grow. The universe has only been around for 13.8 billion years, and gravity can only pull matter together so fast. Structures above a certain size simply should not have had enough time to form. And yet, here is the Hercules-Corona Borealis Great Wall, seemingly violating that limit. Astronomers are still trying to understand how such enormous structures can exist. It may require revisions to our models of how the universe evolved in its early stages. Or it may suggest that our understanding of dark matter and dark energy, the invisible components that make up most of the universe's mass and energy, is incomplete. The point is, at every scale we look, the universe reveals structures larger than we expected. Alcyoneus is the largest single galaxy structure we have found, with its radio lobes extending 16.3 million light-years. IC 1101 is the largest galaxy by stellar extent, spanning 6 million light-years. Laniakea is the supercluster we inhabit, stretching 520 million light-years. The Sloan Great Wall is a filament of galaxies, extending 1.37 billion light-years. And the Hercules-Corona Borealis Great Wall spans 10 billion light-years. Each of these structures dwarfs the Milky Way. Each one makes our galaxy look small, insignificant, ordinary. And yet, the Milky Way is still home. It is still the galaxy that contains the Sun, the Earth, and us. Now, you might be wondering how astronomers measure these enormous distances. How do we know that Alcyoneus is 3 billion light-years away? How do we know that IC 1101 is 1.07 billion light-years distant? You cannot just stretch a ruler from here to Alcyoneus or IC 1101. The distances are far too large for any direct measurement. Instead, astronomers use a series of techniques, collectively called the cosmic distance ladder. Think of it like a ladder, where each rung allows you to measure slightly greater distances, and you need to climb the lower rungs to reach the higher ones. The first rung of the ladder is parallax. This is the most direct method for measuring distances to nearby stars. Parallax works like this. Hold your finger up at arm's length and close one eye. Note where your finger appears against the background. Now, open that eye and close the other one. Your finger appears to shift against the background. This shift happens because your two eyes are viewing your finger from slightly different positions. The same principle works for measuring distances to stars. As Earth orbits the Sun, we view nearby stars from different positions 6 months apart. A nearby star will appear to shift slightly against the background of more distant stars. By measuring this shift and knowing the size of Earth's orbit, we can use basic trigonometry to calculate the distance to the star. The European Space Agency's Gaia satellite has used parallax to measure distances to over 1 billion stars with incredible precision. But parallax only works for relatively nearby stars, those within a few thousand light-years. Beyond that, the shifts become too small to measure accurately. For greater distances, we need the second rung of the ladder, standard candles. A standard candle is any object whose intrinsic brightness is known. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. It is like seeing a light bulb in the distance. If you know it is a 100-watt bulb, you can estimate its distance based on how bright it appears. One of the most important standard candles is the Cepheid variable star. Cepheid variables are stars that pulsate, growing brighter and dimmer in a regular cycle. Henrietta Swan Leavitt discovered in the early 1900s that there is a direct relationship between a Cepheid's pulsation period and its intrinsic brightness. A Cepheid that pulsates with a longer period is intrinsically brighter than one with a shorter period. This discovery was revolutionary because it meant that by simply measuring a Cepheid's pulsation period, you could determine its true brightness. And once you know its true brightness and measure its apparent brightness as seen from Earth, you can calculate its distance. Edwin Hubble used Cepheid variables to measure the distance to Andromeda in 1924, proving it was far outside the Milky Way. The Hubble Space Telescope has observed Cepheids in galaxies up to about 100 million light-years away. For even greater distances, we need an even brighter standard candle. That is where Type Ia supernovae come in. A Type Ia supernova occurs when a white dwarf star in a binary system accretes matter from its companion until it reaches a critical mass. At about 1.4 times the mass of the Sun, the white dwarf can no longer support itself, and it explodes catastrophically. The remarkable thing about Type Ia supernovae is that they all reach approximately the same peak brightness because they all explode at the same critical mass. This makes them incredibly useful as distance markers. Type Ia supernovae are so bright that they can be seen billions of light-years away. They outshine entire galaxies for a few weeks. By measuring the apparent brightness of a Type Ia supernova and comparing it to the known intrinsic brightness, astronomers can calculate distances to galaxies billions of light-years away. This is how we know the distances to galaxies like Alcyoneus and IC 1101. But there is another technique for extremely distant objects, and that is using redshift. As the universe expands, space itself is stretching. Light, traveling through this expanding space, gets stretched along with it. This stretching increases the wavelength of the light, shifting it toward the red end of the spectrum. The more distant an object is, the more space its light has traveled through, and the more redshift it exhibits. By measuring the redshift of a galaxy and using our understanding of how the universe has expanded over time, we can estimate its distance. This technique works for the most distant galaxies, those we see as they were billions of years ago, when the universe was young. Each of these techniques, parallax, Cepheids, Type Ia supernovae, and redshift, is calibrated against the previous one. We use parallax to measure distances to nearby Cepheids. We use those Cepheids to calibrate Type Ia supernovae. We use Type Ia supernovae to calibrate the relationship between redshift and distance. It is a carefully constructed ladder where each rung depends on the accuracy of the rungs below it, and the result is a remarkably consistent picture of the universe's structure and the distances to objects within it. But there is something else we need to talk about when discussing the scale of the universe and the sizes of galaxies. Something invisible that dominates the mass of every galaxy and shapes the structure of the cosmos. Dark matter. Dark matter is one of the great mysteries of modern physics. We know it exists because we can see its gravitational effects, but we have never directly detected it. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is completely invisible to all forms of electromagnetic radiation, from radio waves to gamma rays. The only way we know dark matter is through its gravitational influence on visible matter, and that influence is enormous. In fact, dark matter makes up about 85% of all the matter in the universe. Normal matter, the protons, neutrons, and electrons that make up atoms, and therefore stars, planets, and us, accounts for only about 15%. The rest is dark matter. In the Milky Way, the visible disk of stars and gas that we can see has a mass of about 100 billion solar masses. But the total mass of the Milky Way, including dark matter, is about 1.5 trillion solar masses. That means dark matter outweighs visible matter by a factor of 15 to 1 in our galaxy. And the dark matter is not distributed the same way as the visible matter. The visible matter is concentrated in a relatively flat disk, the spiral structure we can see. The dark matter forms a roughly spherical halo surrounding the visible galaxy. This dark matter halo extends far beyond the visible edge of the Milky Way, reaching out perhaps 300,000 light-years or more from the center. We know this dark matter halo exists because of how stars and gas move in the outer regions of the galaxy. According to Newton's laws of gravity, objects farther from the center of a galaxy should orbit more slowly, just like outer planets in the solar system orbit more slowly than inner planets. But when astronomers measured the orbital velocities of stars and gas clouds in the outer Milky Way, they found something strange. The velocities did not decrease with distance. Instead, they remained roughly constant, even far from the galactic center. This flat rotation curve, as it is called, implies that there is far more mass in the galaxy than we can see. The only way to explain the observations is if there is a massive halo of invisible matter surrounding the visible galaxy. This dark matter halo provides the extra gravity needed to keep the outer stars moving as fast as they do. The same pattern appears in every galaxy we have studied. All galaxies have flat or nearly flat rotation curves, implying all galaxies have dark matter halos. In fact, the masses of galaxies' dark matter halos are directly related to the sizes of the galaxies. Larger halos produce larger galaxies. IC 1101, with its enormous size, must have an incredibly massive dark matter halo. Estimates suggest IC 110's total mass, including dark matter, is around 100 trillion solar masses. That is about 60 to 70 times the total mass of the Milky Way. Most of that mass is dark matter, invisible and mysterious. We do not know what dark matter is made of. The leading candidates are exotic subatomic particles that do not interact with normal matter except through gravity. These particles would have been created in the Big Bang, and they have been around ever since, forming the gravitational scaffolding that allowed galaxies to form. Physicists have built detectors deep underground and in space, trying to catch dark matter particles as they pass through Earth. So far, despite decades of searching, we have not found any. Dark matter remains elusive, detected only through its gravitational effects, but its presence is undeniable. Without dark matter, galaxies as we know them could not exist. The universe would be a very different place, and dark matter is not the only invisible component of the universe. There is also dark energy. If dark matter is mysterious, dark energy is even more so. Dark energy is a property of space itself, an energy that causes the expansion of the universe to accelerate. In the late 1990s, two teams of astronomers studying distant type Ia supernovae made a shocking discovery. They found that the universe's expansion is not slowing down, as everyone expected. Instead, it is speeding up. Distant galaxies are receding from us faster and faster. Something is pushing the universe apart, and that something is dark energy. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, everything we can see, makes up only about 5%. That means 95% of the universe is made of things we do not understand. We do not know what dark energy is. The leading theory is that it is a property of empty space itself, sometimes called the cosmological constant. But we do not know why space has this property or where the energy comes from. Dark energy is causing the universe to expand faster and faster, over billions of years. This acceleration will have profound effects. Distant galaxies are already moving away from us faster than the speed of light. not because they are traveling through space faster than light, but because space itself is expanding between us and them. As the expansion continues, more and more galaxies will cross the cosmic horizon, the boundary beyond which light can no longer reach us. Eventually, in about 100 billion years, all galaxies beyond our local group will have been carried away beyond the horizon. Future astronomers looking at the sky will see only the galaxies in our local group. Everything else will be invisible, carried away by the expansion of space. They will live in a universe that appears much smaller and much emptier than the one we see today. In a strange twist, those future astronomers might come to the same conclusion that early 20th century astronomers did, that their galaxy is all there is. Except they will be even more wrong, because there will be trillions of galaxies beyond their horizon, forever unobservable. Dark energy also affects the formation of large-scale structures. The acceleration of the universe's expansion makes it harder for gravity to pull matter together. Structures like galaxy clusters and superclusters have largely stopped growing. The ones that exist today will remain, but new ones are unlikely to form. The universe has entered a new phase, one dominated by dark energy rather than matter. Understanding dark matter and dark energy is one of the great challenges of modern physics. These invisible components dominate the universe, but we know almost nothing about them. Galaxies like Alcyoneus and IC 1101, with their enormous sizes and masses, are key to studying dark matter. By measuring how galaxies move and interact, by studying the structure of galaxy clusters, by analyzing gravitational lensing, where light from distant galaxies is bent by the gravity of intervening dark matter, astronomers are slowly piecing together the properties of dark matter. And, by studying the expansion history of the universe, by measuring distances to supernovae and galaxies at different epochs, cosmologists are probing the nature of dark energy. The largest galaxies and structures in the universe are not just impressive for their size, they are laboratories for studying the fundamental nature of reality itself. Now, let me tell you about what the future holds for our exploration of the largest structures in the universe. Because the story of Alcyoneus and IC 1101 is not just about what we have found. It is also about what we might find next. Astronomy is advancing at an incredible pace. The telescopes and instruments being built today will see things we can barely imagine. The James Webb Space Telescope, which launched in December 2021, is already transforming our understanding of the early universe. Webb is designed to observe in infrared wavelengths, which allows it to see through dust and to detect light from extremely distant galaxies that has been redshifted into the infrared. In just its first year of operation, Webb discovered galaxies that existed when the universe was only 300 million years old. These galaxies are smaller and more irregular than modern galaxies, representing an earlier phase of galaxy evolution. By studying these early galaxies, astronomers are learning how the first structures formed after the Big Bang. But Webb is just the beginning. The next generation of ground-based telescopes will be even more powerful. The extremely large telescope, being built in Chile by the European Southern Observatory, will have a primary mirror 39.3 meters in diameter. That is almost 4 times wider than the largest telescopes currently operating. With such a large mirror, the extremely large telescope will be able to collect far more light, allowing it to see fainter objects and resolve finer details. It will be able to directly image exoplanets, study the atmospheres of distant worlds, and observe galaxies at the edge of the observable universe. For galaxies like IC 1101 and Alcyoneus, Larger telescopes mean we can study them in much greater detail. We can resolve individual star clusters within distant galaxies. We can measure the motions of stars and gas to understand the distribution of dark matter. We can study the environments around supermassive black holes. Radio astronomy is also advancing rapidly. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the largest radio telescope ever built. It will consist of thousands of individual antennas working together, creating a collecting area of about 0.39 square miles, hence the name Square Kilometre Array. The Square Kilometre Array will be 50 times more sensitive than existing radio telescopes. This means it will be able to detect fainter radio sources, including radio galaxies with lobes even larger than Alcyoneus. It is entirely possible that once the Square Kilometre Array begins operations, it will discover radio galaxies with lobes stretching 20 million light-years or more. Alcyoneus's record may not stand for long. The array will also be able to map the distribution of hydrogen gas across vast regions of the universe. Hydrogen is the most common element, and by mapping where it is, astronomers can trace the cosmic web in unprecedented detail. This will give us a much better understanding of the large-scale structure of the universe and how galaxies are distributed within it. Space-based observatories are also evolving. The European Space Agency is planning a mission called Euclid, designed to map the geometry of the universe and study dark matter and dark energy. Euclid will observe billions of galaxies, measuring their shapes and distances with high precision. By analyzing how galaxies cluster and how their light is bent by intervening dark matter, Euclid will provide new insights into the nature of dark energy and the distribution of dark matter throughout the cosmos. NASA is planning a similar mission called the Nancy Grace Roman Space Telescope. Roman will have a field of view 100 times larger than Hubble, allowing it to survey vast areas of sky quickly. It will study the expansion history of the universe, search for exoplanets, and map the distribution of galaxies in the nearby universe. These missions, and others being planned, will generate enormous amounts of data. The challenge for astronomers is not just building better telescopes, but analyzing the flood of information those telescopes produce. This is where artificial intelligence and machine learning are becoming increasingly important. Modern surveys produce images of millions or billions of galaxies. No human could possibly examine all of them individually. Instead, computer algorithms are trained to identify interesting objects, classify galaxies by type, measure their properties, and flag unusual features for closer examination. Machine learning has already been used to discover new types of galaxies, identify rare objects like gravitational lenses, and even predict the properties of dark matter halos based on the visible galaxies they contain. As telescopes get better and datasets get larger, AI will play an even more central role in astronomy. One particularly exciting possibility is the discovery of entirely new types of large-scale structures. The cosmic web, with its filaments and voids, is the largest known structure. But are there structures even larger? Some theoretical models suggest there could be. If the early universe had certain types of density fluctuations, it could have produced structures on scales larger than the observable universe. We would only be able to see a small part of such structures, but their presence might be detectable through subtle patterns in the distribution of galaxies or the cosmic microwave background radiation. These ideas are speculative, but they are being taken seriously by cosmologists. Future surveys might reveal patterns that hint at structures beyond what we can currently observe. Another frontier is understanding the connection between galaxies and their environment in much greater detail. We know that galaxies in dense clusters evolve differently from galaxies in sparse regions. Cluster galaxies tend to be ellipticals that have stopped forming stars, while galaxies in less dense regions are more likely to be spirals, still actively forming stars. But the detailed physics of how environment affects galaxy evolution is still being worked out. By studying large samples of galaxies in different environments, from isolated field galaxies to galaxies in the densest cluster cores, astronomers are building a comprehensive picture of how galaxies change depending on where they live. IC 1101, sitting at the center of a rich cluster, represents one extreme. The Milky Way, in a relatively sparse region, represents another. By comparing galaxies across this full range of environments, we can understand the factors that drive galaxy evolution. There is also the question of what will happen to these large galaxies in the far future. We have talked about how IC 1101 grew by consuming smaller galaxies. But what happens next? As the universe continues to expand, driven by dark energy, structures will become increasingly isolated. Galaxy groups and clusters that are currently connected by the cosmic web will be pulled apart. Eventually, each cluster will be alone, separated from all others by distances that light cannot cross. Within these isolated clusters, galaxies will continue to merge. Over trillions of years, all the galaxies in a cluster might merge into a single, enormous galaxy. These ultra-giant galaxies would dwarf even IC 1101. But they would be alone in an otherwise empty universe, unable to see or interact with any other structure. This is the ultimate fate predicted by current cosmological models. An empty, cold universe dominated by dark energy with isolated islands of matter that can no longer communicate with each other. It is a bleak picture, but it is also trillions of years in the future. For now, we live in a universe that is still dynamic, still evolving, still full of structures forming and interacting, and we have the privilege of observing and studying this universe in real time. Every discovery, from Alcyoneus to IC 1101 to the Hercules-Corona Borealis Great Wall, adds to our understanding. Every new telescope, every new survey, every new technique reveals more about the cosmos. We are living in a golden age of astronomy. The pace of discovery is accelerating. Questions that seemed unanswerable a generation ago are now being addressed. And new questions are emerging. Questions we did not even know to ask. What is dark matter made of? What is dark energy? How do supermassive black holes form and grow? Are their structures even larger than the Hercules-Corona Borealis Great Wall? Is life common in the universe, or are we alone? These are the questions driving modern astronomy. And while we may not answer all of them in our lifetimes, we are making progress. Each discovery brings us closer to understanding. The biggest galaxy we have discovered, Alcyoneus, is not just a record to be broken. It is a window into the physics of supermassive black holes, relativistic jets, and the intergalactic medium. IC 1101 is not just a giant collection of stars. It is a laboratory for studying galaxy mergers, dark matter, and the evolution of elliptical galaxies. These objects are teaching us about the universe. And the more we learn, the more we realize how much we do not know. That is the nature of science. Every answer raises new questions. Every discovery reveals new mysteries. And that is what makes it so exciting. We will never know everything. The universe is too vast, too complex. But we can keep learning, keep exploring, keep pushing the boundaries of human knowledge. And as we do, we will discover things that amaze us. We will find structures larger than Alcyoneus. We will understand dark matter and dark energy. We will answer the big questions, and we will ask new ones. That is the future of astronomy. That is the future of human exploration. Not exploration with spacecraft, at least not anytime soon, but exploration with telescopes and computers and human minds. Reaching out across the cosmos, studying the largest structures, understanding how they formed and how they evolve. And through that understanding, comprehending our own place in the vastness of space. The largest galaxies and structures in the universe are not just impressive for their size. They are laboratories for studying the fundamental nature of reality itself. And the result is a remarkably consistent picture of the universe's structure and the distances to objects within it. For nearby stars within a few thousand light years, astronomers use parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this shift, you can calculate the distance using basic trigonometry. For more distant objects, astronomers use standard candles, objects whose intrinsic brightness is known. Cepheid variable stars, for example, pulsate with a period that is related to their luminosity. By measuring how bright a Cepheid appears and knowing how bright it actually is, you can calculate its distance. For even greater distances, astronomers use type Ia supernovae. These exploded stars all have roughly the same peak brightness, making them excellent distance markers. They are so bright they can be seen billions of light years away. The Hubble Space Telescope revolutionized distance measurements by observing Cepheid variables in distant galaxies. Hubble allowed astronomers to measure distances to galaxies tens of millions of light years away, with unprecedented precision. The James Webb Space Telescope, launched in December 2021, is pushing these measurements even further. Webb can observe some of the most distant galaxies ever seen, galaxies that formed when the universe was only a few 100 million years old. But here is the thing: all these measurements have uncertainties. The distance to Andromeda, for example, is known to be about 2.5 million light years, but that number has an uncertainty of about plus or minus 100,000 light years. For more distant objects, the uncertainties get larger. When we say Alcyoneus is 3 billion light years away, that is based on measurements that have some margin of error. The actual distance could be slightly more or slightly less. And when we talk about the size of the observable universe, 93 billion light-years across, that is based on models of how the universe has expanded since the Big Bang. We cannot directly measure distances that large. We infer them from other observations, from the cosmic microwave background radiation, from the distribution of galaxies, from the redshift of light from distant objects. Astronomy is hard. Measuring the vastness of space requires careful work, sophisticated instruments, and complex mathematical models. And even then, there is always some uncertainty. But despite these challenges, astronomers have built up a remarkably consistent picture of the universe's structure and scale. And that picture shows clearly that the Milky Way, while large compared to most galaxies, is tiny compared to the largest structures in the cosmos. Let us talk about what all this means. Why does it matter that Alcyoneus has radio lobes stretching 16.3 million light-years? Why should we care that IC one contains 100 trillion stars. On one level, it matters because it teaches us about how the universe works. These enormous structures tell us about the power of supermassive black holes, about the properties of the intergalactic medium, about how galaxies form and evolve over billions of years. But on another level, it matters because it puts our place in the universe into perspective. For most of human history, we believed we were at the center of everything. The Earth was the center of the universe, and everything revolved around us. We were special, central, important. This view was shattered step by step over centuries. Copernicus showed that Earth orbits the Sun, not the other way around. Galileo's telescope revealed that other planets had moons, that the universe was larger and more complex than anyone had imagined. Hubble proved that the Milky Way was just one galaxy among many. And now, we know that the Milky Way is not even a particularly large galaxy. It is comfortably above average, sitting in the top 5% of galaxy sizes, but it is dwarfed by supergiants like IC 1101. And even IC 1101 is tiny compared to structures like Laniakea or the Sloan Great Wall. We are not at the center of anything. We are not special in terms of location or scale. Earth is a small rocky planet orbiting an average star in the outer regions of a large but not exceptional spiral galaxy. That galaxy is part of a small group of galaxies on the outskirts of a supercluster, which is itself part of larger cosmic structures. At every scale, we are ordinary. And yet, despite this ordinariness, despite our cosmic insignificance, here we are, conscious beings, aware of ourselves and our surroundings, capable of studying the universe and understanding our place in it. We can measure the distance to galaxies billions of light years away. We can calculate the size of structures so large that light takes millions or billions of years to cross them. We can piece together the history of the universe from the Big Bang to the present day. That is remarkable. The universe does not care about us. The enormous structures we have been discussing, Alcyoneus and IC 1101 and Laniakea, they exist completely independent of whether we observe them or not. They would be there whether we existed or not. But we do exist, and we have built telescopes and developed theories and conducted observations that allow us to see and understand these structures. We are the universe, looking at itself. We are a tiny part of the cosmos that has become aware of the whole, and that is something worth appreciating. Now, let us return to Alcyoneus specifically, because there are some fascinating details about this galaxy that we have not covered yet. The galaxy is classified as a radio galaxy, meaning it emits strongly at radio wavelengths due to its active galactic nucleus. Radio galaxies are relatively rare. Only about 10% of galaxies have active galactic nuclei producing detectable jets. Of those, only a small fraction have jets powerful and long-lived enough to create lobes extending millions of light years. Alcyoneus is at the extreme end of this distribution. The central black hole is estimated to be around 400 million times the mass of the Sun. That is large, but not exceptional. The black hole at the center of -87 is over 16 times more massive. So mass alone does not explain why Alcyoneus grew so large. The key seems to be a combination of factors: the low-density environment, the steady jet activity, and the favorable orientation. The jets from Alcyoneus are moving at a significant fraction of the speed of light. Relativistic jets like these are among the fastest phenomena in the universe. They carry enormous amounts of energy, and when they slam into the intergalactic medium, they create shock waves that heat the gas to millions of degrees. This heated gas emits X-rays, which astronomers can detect with X-ray telescopes. The interaction between the jets and the surrounding medium is violent and energetic, a cosmic collision happening on unimaginable scales. One interesting question is what will happen to Alcyoneus in the future. The jets are still active, still pumping energy into the radio lobes. In principle, the lobes could continue growing, potentially reaching 20 million light-years or more. But eventually, the black hole will run out of fuel. The supply of gas and dust falling into it will diminish, and the jets will weaken and eventually shut off. When that happens, the radio lobes will begin to fade. The high-energy particles that produce the radio emission will gradually lose energy through synchrotron radiation. Over tens of millions of years, the lobes will cool and dim until they are no longer detectable. All that will remain is the galaxy itself, the main stellar body, and eventually even the evidence of its enormous radio lobes will disappear. In cosmic terms, Alcyoneus's current state is temporary. It is a phase the galaxy is going through, a period of intense activity that will eventually end. Billions of years from now, assuming the galaxy is not disrupted by mergers or other events, it will likely be a quiet elliptical galaxy with no active jets, no radio lobes, nothing to distinguish it as having once been the largest known galaxy structure. This is true of all the giant structures we have discussed. IC 1101 will not remain 6 million light-years across forever. It is still consuming smaller galaxies, still growing, but eventually the supply of nearby galaxies to cannibalize will run out. The Sloan Great Wall and the Hercules-Corona Borealis. Great Wall are filaments of galaxies held together by gravity, but the universe is expanding. Dark energy is causing space itself to stretch, pushing structures apart. Eventually, over trillions of years, these great walls will disperse. The galaxies within them will be carried away by the expansion of space, and the filaments will dissolve. Everything in the universe is temporary. Even structures as enormous and seemingly permanent as Alcyoneus are just phases, moments in cosmic history. And yet, in this moment, right now, Alcyoneus exists. Its radio lobes stretch across 16.3 million light-years of space. Particles accelerated by a supermassive black hole are streaming outward at nearly the speed of light, colliding with the intergalactic medium, creating vast bubbles glowing with radio emission. It is happening right now, even though the light showing us this is from 3 billion years ago. When we observe Alcyoneus with radio telescopes, we are seeing it as it was 3 billion years ago. Light travels at a finite speed, so looking out into space is also looking back in time. 3 billion years ago, complex multicellular life was just beginning to diversify on Earth. The supercontinent Rodinia was forming. The first animals were still hundreds of millions of years in the future. And in a distant corner of the universe, a galaxy we would one day name Alcyoneus was producing jets that would stretch across 16 million light-years. That light has been traveling through space for 3 billion years, crossing unimaginable distances, until finally it reached Earth in the 21st century, where astronomers using radio telescopes detected it and realized they had found something extraordinary. By now, 3 billion years later, in Alcyoneus's own timeline, the galaxy may have changed significantly. The jets may have shut off. The lobes may have faded. The galaxy may have merged with another galaxy, completely altering its structure. We have no way of knowing what Alcyoneus looks like right now, because the light showing us the present-day Alcyoneus will not reach Earth for another 3 billion years. This is the strange nature of astronomical observation. Everything we see is from the past. The deeper we look into space, the further back in time we are looking. The most distant galaxies we can observe are seen as they were more than 13 billion years ago, when the universe was only a few 100 million years old. Those galaxies may not even exist anymore, at least not in the form we see them. They may have merged with other galaxies, forming larger structures. They may have been torn apart by gravitational interactions. We are observing their ancient light, but we are cut off from their present state by the vast distances involved. This is one of the fundamental challenges and one of the profound aspects of astronomy. We can observe the universe across enormous stretches of space, but we cannot observe it across time. We are always looking at the past, never the present. So when we talk about Alcyoneus being the biggest galaxy we have discovered, what we really mean is, it is the biggest galaxy structure we have detected so far, based on observations of light that left it billions of years ago. There may be larger structures out there that we have not found yet. As radio telescopes improve and we survey more of the sky, we will likely discover more enormous radio galaxies. Alcyoneus may hold the record for a few more years, or it may be dethroned by an even larger structure discovered tomorrow. The universe is vast, and we have only scratched the surface of exploring it. But even if we find larger structures, even if Alcyoneus is eclipsed by something even more enormous, the fundamental point remains. The universe operates on scales that are difficult for human minds to comprehend. 16.3 million light-years. 6 million light-years. 10 billion light-years. These are distances so large they become abstract. We can calculate them, plot them on charts, compare them to each other, but truly grasping what they mean is nearly impossible. Our brains did not evolve to understand cosmic scales. They evolved to understand the immediate environment, the scale of a few miles, the time scale of a few decades. Trying to comprehend structures millions or billions of light-years across is like trying to visualize a number with 1 trillion digits. You can acknowledge it intellectually, but you cannot truly hold it in your mind. And yet, despite these limitations, we keep trying. We build bigger telescopes. We develop better theories. We push the boundaries of what we can observe and understand. And slowly, step by step, we are mapping out the universe's structure. We have discovered that galaxies come in all sizes, from tiny dwarfs to supergiants like IC 1101. We have learned that galaxies cluster together into groups and superclusters, which themselves form filaments and walls stretching across billions of light years. We have found that some galaxies have radio lobes extending millions of light years beyond their visible bodies, making them far larger than their stellar components alone would suggest. And we have realized that the Milky Way, our home galaxy, while large compared to most galaxies, is small when compared to the true giants of the cosmos. That realization can be humbling. It can make us feel insignificant, tiny, unimportant. If the Milky Way is just one galaxy among 2 trillion, and if it is small compared to galaxies like IC 1101 and structures like Alcyoneus, what does that say about us? What does it say about Earth, a small, rocky planet in the outer reaches of a not particularly special galaxy? One way to respond to this is to feel despair, to conclude that we are meaningless specks in an unimaginably vast universe that does not care about us. But there is another way to look at it. Yes, we are small. Yes, The universe is vast. But we are here. We exist. Against all odds, on this small planet, in this ordinary galaxy, life arose. Not just life, but complex life. Multicellular organisms, animals, eventually humans. Conscious beings capable of looking up at the night sky and wondering what is out there. We built telescopes to see farther. We developed mathematics to understand what we see. We sent probes beyond our solar system, carrying messages from humanity into the cosmic ocean. We are the universe's way of knowing itself. We are a small part of the cosmos that has become aware of the whole, and that is extraordinary. The fact that we are small does not make us insignificant. If anything, it makes our existence more remarkable. Against the vast emptiness of space, against the overwhelming scales of galaxies and superclusters, here we are. A tiny island of complexity and consciousness in an ocean of mostly empty space. So yes, Alcyoneus is enormous. Its radio lobes stretch for 16.3 million light-years. IC 1101 contains 100 trillion stars. The Hercules-Corona Borealis Great Wall spans 10 billion light-years. These structures dwarf the Milky Way, and they dwarf Earth even more completely. But they also make what we have here even more precious. As far as we know, Earth is the only place where life exists. We have searched for signs of life on other planets, and we have found nothing conclusive. We have listened for radio signals from other civilizations, and we have heard only silence. Maybe life is common in the universe, and we just have not found it yet. Maybe it is rare, and we are alone, or nearly so. We do not know. But we do know that life is here on Earth. And that makes this small planet, orbiting an average star in an ordinary galaxy, incredibly special. Not special in terms of size or location, but special in terms of what it contains. Life, consciousness, art, music, love, curiosity, the capacity to wonder about the universe and our place in it. Those things do not depend on size. They depend on complexity, on organization, on the remarkable fact that matter can arrange itself in ways that give rise to thought and feeling. So when you look up at the night sky tonight, when you see that faint band of light that is the Milky Way, remember this. You are looking at your cosmic home, a galaxy containing hundreds of billions of stars, stretching 100,000 light-years from edge to edge. It is enormous by human standards, but small compared to giants like Alcyoneus and IC 1101. It is part of the local group, which is part of the Virgo supercluster, which is part of Laniakea, which is part of the cosmic web of filaments and voids that makes up the large-scale structure of the universe. At every scale, we are small, but we are also here, alive, aware, curious, reaching out to understand the universe that contains us. And in a cosmos filled with mostly empty space and mindless matter, that is something extraordinary. The biggest galaxy we have discovered is bigger than your imagination. Alcyoneus, with its radio lobes stretching 16.3 million light-years, is a structure so vast it challenges human comprehension. But it is not the only remarkable thing in the universe. You are remarkable too. The fact that you exist, that you can think about these questions, that you can feel awe at the scale of the cosmos, that is just as extraordinary as any giant galaxy. Size is not everything. What matters is what we do with our time here, how we treat each other, what we create, what we discover, what we leave behind. The universe is vast, but it is also beautiful. And you get to be part of it. if only for a brief moment in cosmic time. That is a gift. Make the most of it. There is something profound about standing under a night sky and looking up at the stars, knowing what you now know. Every point of light you see is a sun, perhaps with planets orbiting it. Some of those planets might harbor life. We do not know. The faint band of the Milky Way, stretching across the sky, is not a cloud or a mist. It is the combined light of hundreds of billions of stars, so distant they blend together. That band is your home galaxy, seen from inside. And that galaxy, as enormous as it is tiny compared to giants like Alcyoneus and IC 1101. It is one galaxy among 2 trillion in the observable universe. But it is also the only galaxy we have. It is the only place we have ever been. Every human who has ever lived here, in this galaxy, on this one small planet, in the outer reaches of one spiral arm. We have sent probes beyond our solar system. Voyager 1 and Voyager 2 have crossed into interstellar space, the space between stars. But they are still within the Milky Way. They will remain within the Milky Way for tens of thousands of years as they slowly drift through space. We have looked at distant galaxies with our telescopes. We have studied their light, analyzed their spectra, measured their distances. But we have never been to another galaxy. We never will, not with current technology. The distances are simply too great. Andromeda, our nearest large galactic neighbor, is 2.5 million light-years away. With current spacecraft, it would take billions of years to get there, and that is the nearest one. Most galaxies are billions of light-years away. Alcyoneus is 3 billion light-years distant. We will never visit it. We will never see it up close. All we have is the light that left it 3 billion years ago, finally reaching us now after an unimaginable journey across space. And that is okay. We do not need to visit these places to appreciate them. We do not need to stand on a planet in IC 1101 to understand its size and significance. We can study them from here, from our small planet in our modest galaxy. We can build telescopes and develop theories. We can measure and calculate and compare. And through these efforts, we can understand the universe, even the parts we will never reach. That ability to comprehend things far beyond our direct experience is one of the remarkable features of human consciousness. We are not limited to understanding only what we can touch or see with our own eyes. We can understand the universe in its entirety, from the smallest subatomic particles to the largest cosmic structures. We can grasp the size of Alcyoneus, even though we will never see it, except as a faint smudge of radio emission in our data. We can understand the formation of IC 1101, even though it is over 1 billion light-years away. We can map the cosmic web, trace the flow of galaxies, and measure the expansion of the universe itself, all from this one small planet. That is extraordinary. Throughout this journey tonight, we have talked about scale, about how the Milky Way compares to giants like Alcyoneus and IC 1101, about how galaxies cluster into groups and superclusters, about how the universe is structured as a vast cosmic web, and at every level, the Milky Way appears small. But size is only one way to measure significance. What matters is not how big something is, but what it contains and what it produces. The Milky Way is not the biggest galaxy, but it is the galaxy that produced the Sun. The Sun is not the largest star, but it is the star that made Earth habitable. Earth is not the largest planet, but it is the planet that gave rise to life. Life on Earth is not the most common thing in the universe. Matter is far more common, empty space even more so. But life has produced consciousness. Consciousness has produced curiosity, the desire to understand. And that curiosity has led us to study the universe, to build telescopes, to discover galaxies, to measure their sizes and distances. In the entire observable universe, as far as we know, this has only happened here, only on this one small planet orbiting this one average star, in this one not particularly special galaxy. That makes us rare, possibly unique. We might be the only conscious observers in the entire cosmos. Or we might be one of many. We do not know. But either way, the fact that we exist, that we can think and wonder and discover, that is significant. Size does not determine significance. Alcyoneus is enormous, but it is not aware of its own size. It does not know it exists. It does not wonder about its place in the universe. We do. We are smaller, but we are conscious, and that makes all the difference. There is a concept in astronomy called the anthropic principle. It states that the universe must be compatible with the conscious life that observes it. The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, all of these are finely tuned in a way that allows stars to form, planets to exist, and life to emerge. If any of these constants were slightly different, the universe would be very different, possibly unable to support life at all. Some physicists and philosophers argue that this fine-tuning is evidence of design, that the universe was made for life. Others argue that we exist in a multiverse, an infinite collection of universes with different physical laws, and we naturally find ourselves in one where the constants allow life to exist. We do not know which interpretation, if any, is correct. But what we do know is that we are here, in this universe, able to observe and understand it. And that is remarkable. Regardless of the explanation, the universe did not have to be understandable. The laws of physics could have been chaotic, random, impossible to decipher, but they are not. They are orderly, mathematical, comprehensible. Einstein famously said that the most incomprehensible thing about the universe is that it is comprehensible, and he was right. There is no obvious reason why the universe should be governed by elegant mathematical laws that humans can discover and understand. But it is, and we have. Through centuries of observation and thought, we have pieced together the structure of the cosmos. We know how stars form and evolve. We understand how galaxies grow through mergers and accretion. We have discovered dark matter and dark energy. We have measured the age and size of the universe. We have found the biggest galaxy structure, Alcyoneus, stretching 16.3 million light-years. All of this knowledge, accumulated over generations, is a testament to the power of human curiosity and intelligence. We are small. Our galaxy is small compared to the largest galaxies. But our understanding is vast, and that understanding is growing. Every year, we build better telescopes. We develop better theories. We discover new phenomena, new structures, new mysteries to solve. The James Webb Space Telescope, launched in 2021, is already revealing galaxies that formed when the universe was only a few 100 million years old. These early galaxies are different from the galaxies we see today, smaller and more irregular. By studying them, we are learning how galaxies evolved over cosmic time. Future telescopes, even more powerful than Webb, will see even further back, closer to the Big Bang. They will find even more distant galaxies, even larger structures. Our map of the universe will continue to expand. And with each new discovery, our perspective shifts. We realize we are even smaller, even less central than we thought. But we also realize we are part of something magnificent. The universe is vast, complex, and beautiful, and we get to explore it, to learn about it, to marvel at it. That is a privilege not to be taken lightly. So yes, the Milky Way is small compared to Alcyoneus. It is small compared to IC 1101. It is a tiny part of Laniakea, which is itself a small part of the cosmic web. At every scale, we are dwarfed by larger structures. But we are also here, aware, curious, striving to understand. And in a universe made mostly of empty space and mindless matter, that is something truly special. The biggest galaxy we have discovered is bigger than your imagination. Alcyoneus, IC 1101, the Hercules-Corona Borealis Great Wall. These structures challenge our ability to comprehend scale, but they also inspire wonder. They remind us that the universe is far stranger and more magnificent than anything we could have invented. And they remind us that we are part of this cosmos, connected to it, made of the same matter that makes up stars and galaxies. We are the universe, experiencing itself. We are stardust that has become conscious. And that is worth celebrating. When you look up tonight, remember this. You are standing on a small planet in a large but not exceptional galaxy. That galaxy is part of structures spanning millions and billions of light years. The universe is vast, beyond comprehension. But you are here, alive, aware, able to understand and appreciate the cosmos. And that makes you, and everyone else on this small planet, truly remarkable. The universe gave us this gift: consciousness, curiosity, the ability to wonder. Make the most of it. Keep looking up. Keep asking questions. Keep learning. Because that is what makes us human. That is what makes us special in a universe full of giants. That is a gift. Make the most of it.